We are ready to kick off with our first speaker, Pim. So everyone, huge rounds of applause for Pim de Wit. Woo!
Thank you.
There you go.
Hi everyone. I'm very nervous, so I've got my emotional support water bottle right here. Here we are. My name is Pim. I am since recently a design engineer at Granola. I've been in the game for about 15 years, mostly working on more creative applications. So that is a lot of game development, a lot of kind of like experiential experiences, I guess. Lots of WebGL, WebGPU, and all of that. Today, I would like to share, one of my favorite programming philosophies, which is data-oriented design. Before I get into that though, I quickly want to show a demo that I've made for this talk, which is basically a small Where is Waldo game. And apologies, I recently got told that it's actually Where's Wally in the UK. I know it is as Waldo. So in this game, you get a couple cards with characters that you have to find. So let me zoom in a little bit. And you basically have to find them just across all of these different characters over here. So you can click on one. Sorry, we're already on mobile. Give me a hint. So check out east. We've got a little compass in the bottom right. They like the high ground. Okay, so they're somewhere up high. So the east is right over here. Oh, I think I see them. There they are. Woo, nice. Let's do one more. Northeast, high ground again. Look near the flowers, and they keep to themselves, so they're likely not in a group. So we're already looking northeast-ish. Do let me know if you see them. Oh, here we go. So that's the game. And if I go back just one page, I've basically made a tech demo showing, this is a little bit of a spoiler for what's about to come in the talk, but showing how we can basically render a lot of these characters at the same time. So right now it is 1020. Let me turn off that wobble actually, just so we don't get motion sick at the end of this. We can have 50,000 of these rendering at the same time. So if I just zoom in, here's our randomized characters. And hopefully at the end of this talk, you'll get a little bit of an understanding of how this is basically almost free to render and to compute. Throughout the talk, I will be using the DevTools quite a bit, and in particular the performance panel. So I do this to basically profile my application, and then you can basically see how much CPU and how much GPU is being consumed every single frame. So in this case, for all 50,000 characters, it is about 0.16 milliseconds, which is very, very tiny. On most machines that run at 60 FPS, you have a budget of 16 milliseconds, and all of this is currently rendering at 0.16. So very, very fast. And the GPU in this case as well, 0.14 milliseconds. So, the characters themselves, they're basically just made in Figma, it's very crudely drawn. I literally did it in like 5 minutes. And these are basically the parts that I'm randomizing for the characters. Let me take a sip of water. And if I was asked, like, how do you start this logic? How do you create the data for these characters? Historically, I would do something like this, where each character is basically an object, and they've got an X and Y position in this case. Can everyone see that all right, by the way? I know that I'm right in front of you. Okay. Maybe there's like a string or an image for the eyes and the body. And in this case, 50,000 characters get pushed to a characters array. So an object for every character. If I'm feeling really fancy, maybe that would even be a class. But this is really slow at this scale. I've created two benchmarks just to show how slow objects actually are and what I would recommend doing instead when you're working with really big data. So don't look at the code just yet. I'll just show that in a second. I've created this demo right here, which is 260,000 rectangles that are basically animating X, Y, width, and height properties every single frame. So if we do a profile of this, you will see that this is completely clogging up the CPU. So this runs at 12.5 milliseconds. I'm on a fancy MacBook Pro, so I've got 120 FPS, which means that we're dropping frames. As shown here as well, instead of 120, it is showing 80 FPS. And this is basically animating objects. Here's the code for it. So I've got an array of rectangles, an array for my rectangles. Then I have a for loop, where the count in this case is 260,000. I create an object for each, or a rectangle for each of these iterations. So a rect, which is an object with X, Y, width, and height. And then I push that to the rectangles array. And then later on in my render loop, I would loop through my rectangles again, and then basically just change the X, Y, width, and height properties. So this is what I would do if I would normally write code. I think this is kind of like the basics almost of programming, especially for the web. And this is called an array of structures, this pattern. So it is an array of objects that we're iterating through. The second demo, again, don't look at the code just yet, is a structure of arrays. It is the exact same code, with the only change being that instead of objects, we use arrays for the shape of our data. And if we do another profile over here, we will see that instead of 13 milliseconds, it is roughly 4 milliseconds. So it is basically 3 times faster just by using arrays instead of objects. So in this code over here, I guess the whole tactic is that you would create an array for each property that you would normally have in your object. So before we had a rectangle with X, Y, width, and height. In this case, we've got an array for each of these properties. So an array for X, an array for Y, array for width, array for height. In this case, they're 260,000 entries big. And in the render loop, we basically just use the index almost as the rectangle itself, where we just randomize the position slightly. And that alone is such a big difference in computing power. In the objects ones, we're basically dropping frames quite a bit. And again, array of structures versus structure of arrays. And just to illustrate this a little bit better as well, I've got an array with 6 elements in this case. And rectangle in this case doesn't become an object, but it basically becomes an index. Or in this specific context, it's also known as an identity. We take the index of the rectangle and we basically change the value in that column almost. So this would result in the array looking like this. Again, very sorry if you can't see it. But why is this so much faster? So it's basically like a shop that sells eggs by the carton. Even if you just want to get one egg, you will have to buy an actual carton of eggs, right? And this is exactly how the CPU works. So if you get the first index or the first entry of an array, you actually get like 8 different values that you can read and write to for absolutely free. And this is called a cache line. So how many eggs do you actually use? If you use structure of arrays, so basically the pattern where I just had arrays of numbers, you can pack a lot of numbers in a single cache line, and you can change all of these values for the price of 1. If you use objects, these objects are basically references of themselves. So just to complete the analogy, it would basically be like you get the carton, but then the CPU in this case opens up the carton just to have a post-it note saying like, actually the eggs are in the cupboard and in the fridge and all that. So on your computer's cache, this is a lot less optimal. But that doesn't mean that in this case it's 8 times slower. Of course, your CPU does a lot of fancy tricks under the hood to make your code faster, but it does have an impact. one cache line is usually about 64 bytes. On M-chip MacBooks, one cache line is 128 bytes. So if we have one integer of 1 byte, we basically get 128 values that we can change for free. So here are some typed arrays. So the value of your numbers, or even just all your data, they have different sizes in bytes, right? So an 8-bit integer, so an integer from 0 to 255 is only 1 byte. A 32-bit float is 4 bytes. And this has a direct influence on the performance of your runtime code. Now, again, this does not mean that a float is 4 times slower than an integer. There's a lot of stuff happening under the hood that optimizes this, but it does consume 4 times the memory, which is a big factor into your performance as well. So obviously, not all your data can just be numbers. So how do you deal with other data types? What I personally really like to do is I like to keep a map where the number, we still use numbers, as the key to whatever resource I have. So whether that's a string, weirdly enough, or whether in this case it's an image, I basically give it a number that we can then reference in the future in our runtime code. So it's almost like a cloakroom, I guess, where if you would give your jacket or maybe a backpack, the person behind in the cloakroom, they would not actually remember your face or try to get your name or whatever. You get a number, right? And whenever they get that number back, they will just give whatever you gave them in return. So that is basically this pattern over here. And as you can already kind of tell, the readability of this becomes a little bit worse. I personally really like to somewhat solve this with enums. I know that they're a little bit controversial in the web scene, but you can actually name your indexes for all of the different assets that you have. So instead of having to remember, oh, number 1 is the sunglasses, we can actually just name these numbers. So should I stop using objects? Absolutely not. Please do not do that. This is a super handy pattern, structure of arrays that is, for really large data and where you really have to do things at bulk. However, as I mentioned before, readability is kind of trash, right? Like I cannot imagine sharing this with my team of 10 people, let's say, and everyone just being up to date with what is happening and all that. However, there is another pattern called ECS, or Entity Component System, that is super, super useful for managing your data, and it almost like by design encourages you to use very small data shapes. So it's almost like optimized for the cache line just by using it. You can kind of compare it to like a state machine, like Zustand. I'm not going to dive too much into this, but it is honestly so much fun. It has changed my entire perspective on programming in general. I personally use BitECS, which is one of the many libraries that are available. But there's also Miniplex, which is compatible with React, for example. And Kuta is part of the Poimandres family, if I pronounce that correctly. So that's in the same kind of family as React Free Fiber and stuff like that. So back to the game. This is basically the data shape for the game. So we've got an X and Y position. They're both 16-bit integers. Body, head, eyes, mouth, face, but also stuff like elevation, which is generated by the terrain. So how high should something be? And a wanted slot is an 8-bit integer. In this case, there's zeros and ones. If it's a 1, that means that this is one of the characters that you have to find. And a whole character in the end is 23 bytes. So let's go back to the demo. I will have some more visual stuff to show in a second, don't worry. So we'll go back to 50K. And I've been kind of cheating a little bit because all of this data is only prepared once at the very start, and then the data is stagnant. Like nothing is animating, it is just a bunch of dudes hanging around. And just to remind you, so currently this is running at roughly 0.25, but we can make them walk around, So all of our guys are now, sorry, let me adjust this camera, walking around, they're aware of the elevation, and there's a little bit of like collision detection as well, just to make sure that they don't run off the map. There we go. So now we're actually animating X and Y values for each of these characters, so 50,000 times. Let's do another profile while they're all walking. So it has stepped up quite a bit. Instead of 0.2 milliseconds, this is now 1.9 milliseconds. But for all the stuff that's happening here, that is still not that much. Like collision detection, there's like elevations that come into play, and there's no like weird game dev smoke and mirrors happening here as well. One technique that is very popular is culling, that stuff that is not on the camera you just don't render. That is not the case here. Everything just renders as it is at all times. This demo in particular was specifically made with very heavy CPU usage, just to kind of show off what the benefits are. But it also works really well with web GPU. So here's a little demo where I did like a physics simulation. It is 2,000 particles only, and each particle is aware of each other. So the mass behind this, each particle looks at the velocity of all the other particles and their position, and tries to keep like a certain distance between them and whatnot. And if we look at this, so just to clarify, each particle, all 2,000 particles are looking at each other recursively, like all of them. So that is about 12 million operations, math operations per frame. And if we look at the CPU, it is absolutely nothing, 0.10 milliseconds. And most of this 0.10 milliseconds is actually the browser having to do a little bit of bookkeeping, like making sure that the animation loop runs at the same time. Our actual code is only 7 microseconds, and that is for this simulation. But again, there is some stuff happening on the GPU. Most of this data is prepared on the CPU, and then it is passed to the GPU to alter, to manipulate. And this is yet another kind of really big plus point, I guess, on using arrays as your data. WebGPU and WebGL as well, actually, they both run off flat arrays of data. So sometimes they're called buffers. And this is the only way really to send data from your CPU to your GPU. So in this case, I'm sending the X, Y, and Z arrays to my GPU. And then in WebGPU, I can basically read it. And if you use objects, normally you would have to flatten your data before you can send it to WebGPU. And it makes stuff like this very, very fast. One last demo, I think. This is a clone, almost, of Vampire Survivors. Can I get a hands up? Who knows that game? Vampire Survivors? Okay, only a couple. It's basically a game where you just get overwhelmed with enemies and stuff coming at you at all times. And in this case, we've got 50,000 of these little guys, I guess. And they are once again kind of like smart particles. I'm going to move a little bit to the right. These are not just particles that go towards the player. They actually push each other. They're aware of each other's existence. So again, from a maths point of view, there's quite a bit going on. And if I zoom out, there's also quite a bit of them. So let's go back to the profiler. This example is using multi-threading. So we're actually doing our CPU work across different cores. So as usual, let's check out our CPU usage. 0.24, basically free. But if I'm going to zoom this out a little bit, we've got a couple workers over here that I'm going to expand. So your machine comes with several cores. And what that means is that logic can run in different threads. How do I explain that? Of your machine. So basically you can delegate the work that you do across different mini CPUs, I guess is my design vision on it. So each worker in this case, each thread is doing 1.7 milliseconds of work. So we take a lot of data and we basically delegate it. And if I do 2 workers, for example, instead of 8, so right now we've got 8 workers running, we will see that if I zoom in, it is now taking 7 milliseconds per worker. And this is another kind of like hidden bonus that you get from working with arrays instead of objects, because there's an API called a shared array buffer. Do I have a slide on this? Let me have a look. No. So a shared array buffers is relatively new. It allows you to share an array with different cores of your machine. So all your different cores can read and write to the same array. And that is insane. That allows you for stuff, you know, that is not even imaginable in terms of performance. Yeah. Oh, to summarize, this is basically just a list, to be honest, of just terms. If you work with AI agents, you know, these are kind of like the things that you want to tell your AI. Or if you want to do your own research, of course, that's even better. These are some of the things that I've covered just now. And yeah, I think with just a simple change, you can really unlock things that have not been possible before on the web. And especially mixed with Web GPU, I think like stuff like AAA games is very, very close. Thank you.
All right, we're gonna have some questions. Has anyone got any questions? Put your hand up. I'll let Pim choose as well. Don't be shy.
Yes, go for it.
Oh.
With your last example with the sort of vampire survivors clone,
Yeah.
you mentioned how you're delegating work to several workers.
Yeah.
How do you avoid issues with work being split up? Let's say you have 2 adjacent enemies and they need to be aware of each other, and you get delegated to 2 separate workers. How do you avoid race conditions or other issues where maybe one of them checks for collision, the other one's checking for collision with the old position after the previous worker's already moved it?
That's a really good question, and you're kind of calling me out as well on this, because of the sheer volume of this, not every single particle is exactly aware of all other particles. There is an API called Atomics, which allows you to wait for a worker to complete. So it is not completely, that basically eliminates a race condition in this case, but that is more of an architectural question, I think, because in this case I did like, okay, let's say we've got 4 workers and 40,000 entities, 10,000 get done in each worker. But yeah, definitely check out Atomics. That allows you to actually wait for work to complete, but still within the same frame. And yeah, that is what I would recommend there. Yes, Luke.
What are your favorite resources? Because obviously, like, a bunch of us will just slap those terms into Cursor or our agent, whatever we choose. But if we did want to do our own research, are there any places online that you tend to go to that are good?
So especially because I am focused on the web, performance to this level is never really a requirement for most web developers. So definitely the game development industry actually has a lot of resources on this. This pattern is actually almost like a staple of game development, just because there's so much stuff happening at all times. Also some other programming languages like Rust and Zig and Odin, they rely a lot on stuff like this. So I think for the very, very start, data-oriented design is a term by Mike Acton. It was a talk in, I believe, 2014. And that's basically where he started exploring how to really have data as bytes and whatnot. And also, honestly, ECS, bit ECS, is a great resource, and it touches on a lot of these things as well. That is bitecs.dev.
Nice.
Any other questions? Yes.
Curious about ECS, like have you used it like in non-video game apps before?
I have tried. I've definitely tried. So I think it gets a little bit awkward with data that is not runtime or isn't in a loop, basically. I think there's definitely some exploration that can be done there. I believe that the author of Flex is yes. I think that they did some explorations with how to mix it with things like UI. But yeah, that is indeed something that is basically a gap in the market. So if you've got any ideas, go for it. Amazing.
All right, round of applause for Pim.
Thank you.